Okay, so in the event that you happen to watch this video from home, this is just a recap of the work energy theorem. So yesterday I went through and I showed you this, and I'm just going to do this on the recording so people can see it. Work energy theorem, again, is just that the total work is equal to the change in KE. If I don't store work, if I don't lose work, anything extra turns into energy of motion. Now, I wrote this out with you guys yesterday. I'm just going to pull out some equations from the side. We're using F is equal to M times A. And I'm just going to replace A with F over M. And then when I go through and do this, all I'm doing is I'm combining that with this equation. And that equation, again, is just this is what you call solving a system of equations with two unknowns. And when you do a separation of variables and you replace one with the other, you get to this final equation that basically says that the total work that we do on an object changes the kinetic energy. That derivation, I went through that in detail yesterday with you. This is for that recording. Okay, so work net is equal to delta KE. What I wanted to do today is, and I ran out of time yesterday, was to show you how to apply this to example of a bow and arrow kind of thing. Okay, so we know that you guys know that the force exerted from the bow on the arrow is a variable force, correct? I think I actually had a group in here when we were measuring how much work was done to stretch something, and someone had the bow, I think, as an example. But that force is variable. So all I'm going to do here is I'm going to apply the work energy theorem to be able to do it. And again, this is continuation from fifth hour yesterday, just ran out of time. That force, I can get an average value. I'm going to put a line over top of that to say that's an average value. It's acting through a displacement D. And both of these things here are measurable. How far I pull that thing back and how much force I'm exerting, those are measurable things. Well, what that does is it gets deposited into kinetic energy. The work energy theorem says that any work that I do, force through distance, gets deposited as KE. So it's like I'm doing some work and putting it into KE. I would like to determine the average force. So if I start with this equation, I'm going to show you how streamlined I can solve a very complex problem. I can do it very simply using the work energy principle. This net work is net force acting through some displacement D, and that is equal to 1/2 mv final squared. Now this thing starts from rest, so that arrow has no energy to begin with, and after it's acted on by that force of the string through that displacement, it acquires kinetic energy. Now I'm looking for that force. Would you guys agree that the only appreciable force on this thing is the force the string exerts on the arrow? I don't care that there's gravity acting and stuff like that. That gravitational force, would you agree that gravitational force doesn't do work on the arrow? If they're shooting it horizontally? Gravitational force isn't doing any work anyway. So this is the force from the string. Multiplied by the distance is just 1/2 mv final squared. I'm looking for the force from the string, so all I'm going to do is divide the kinetic energy it acquired by the distance through which that force acted. And very quickly, I can get a sense of how much force I have acting by using the work energy theorem. Now, technically speaking, this is an average force, so I'm going to put a bar over top of that. Let's see. I gave you some mass, a mass of the arrow. What would be the mass I put in for this thing? Will you take a look at that and tell me what has to go in there? How much is it? Thank you, 55 grams. But if I want to get force measured in newtons, which is what I want, I have to make sure that that mass is put in kilograms. So one of the things that you'll have to pay attention to is make sure you use the appropriate unit for the quantity that we're looking for. So 1/2 the mass in kilograms. What speed should we use? I gave you feet per second, I gave you miles per hour, I gave you meters per second. What speed should I use? The meters per second. And what was that? Because I can't see it, you guys can? 67 meters per second? Okay, so if I'm using the appropriate units, then the numerator would turn out to be joules. The denominator has to be measured in what unit to be able to get force out of that. To be able to get newtons out of that. What did I give you for the draw length? 65? It needs to go in meters, right? So when I put that in 0.65 meters, I will get then the average force that that arrow is acted upon by that string. And folks, I'm telling you, that equation is very straightforward calculation. I don't have to use F equals m times A. I don't have to use kinematic equations. I'm just using work energy principles. Now, if you have a calculator handy, I can do that with you. 0.5 times 0.055 multiplied by 67 squared, and then divide that. Oh, by the way, the numerator is 123 joules. Divide that by 0.65 meters, and we get that the average force is about 190 newtons. Now, for those of you that are interested in pounds, I'm going to divide that by 4.45, and that would be about 42 pounds of average force. Do you guys agree that the force that the bow is having to exert as you draw the thing back, the force grows? The maximum would be closer to about 80 pounds, and that's because that's about an average value. And so that'd be about a draw strength of about 80 pounds. 0, 20, 40, 60, 80, up to there, and then the average would be about 40. I'm going to ask you guys to try to determine the impact force that the arrow has on the bale of hay. It leaves the arrow, or leaves the bow with 123 joules of energy. It now hits that bale of hay, and it deposits that energy into other forms, but I'd like to determine the impact force. So, first of all, which way does the force act on the arrow to stop it? It acts towards the left. Would you guys agree that that force is going to be really big? It's having to act through a really small distance. So if the amount of work that has to be done is the same, that force and displacement sort of like play inverse roles there. The smaller that displacement is, the bigger that force is to be able to stop that thing. Can you go through and try to calculate that? What is the average impact force for that arrow on the bale of hay? You try it. You guys see that it's the exact same algebraic work. Instead of me doing positive work on the arrow to increase its kinetic energy, the bale of hay is going to do negative work, and it takes all that energy away. So the only thing different here is that the displacement is much smaller. So that that 42 pounds of average force, 190 newtons of average force, turns into what when it hits? Is anyone able to calculate that for me? Thank you. Roughly 4,400? 2,400, thank you. 2,400-ish or so newtons. Okay, so that impact force becomes quite a bit larger. If I wanted to put that in pounds, divide that by 4.45, that's roughly 540 pounds. So when that thing hits, it hits with a decent amount of impact force. Now, of course, if I'm shooting an arrow, I want the arrow to be pointed, and the reason for that is that pressure is a force per unit area. So if I make that area really small, that pressure becomes really big, and that's what's needed to puncture that target. Okay? Work energy principles. Now, folks, I gave you some problems for you to try, and I want to go back to this for a few minutes. the work energy theorem problems, there's a few of them out there. Do your best on going through and solving those. It's what, 1, 2, 3, 4, there's 5 problems. Those are for tomorrow. If I had not done the review with you yesterday, and I spent a decent amount of time doing a review with you, I probably would have been able to assign that yesterday. But I felt like we needed some time after the 2 weeks off to do some review of things. So that's for tomorrow. Now, for today, what I was looking for is I wanted to move into these things called conservative and non-conservative forces. So I want to take a moment and relook at my agenda. So for this one, some problems to try. You got that? We got to look at conservative, non-conservative forces today. This is not a political thing, right? So I'm not talking about conservative versus liberal kinds of things. This is about conservative forces. It's the foundation for developing and applying the law of conservation of energy. And then we're going to connect conservative forces to potential energy. There's gravitational potential energy, there's elastic potential energy, but there's no friction potential energy. There's no energy associated with friction. We'll look at that. We're going to look at something called mechanical energy definition, and then I'm going to start to show you how we use conservation laws. There's some classic demonstrations that I'm going to do with you today on conservation of energy. And so I'd like to get to that. The demonstrations help us understand the concepts. First, we have to define conservative force. If the work done by that force is independent of the path taken, if it doesn't matter what path I take, the work done by that force is independent of the path, we would say that that force is conservative. Another way to look at that is that the work done would be 0 when you move an object through a closed loop. When I take an object and move it through whatever loop that I want, if I go back to the starting point, the total work done by that force is 0 over the entire path. That's how we define conservative forces. Now, the conservative forces in nature. Gravity is a conservative force. So gravitational force is conservative. The work done by the gravitational force as I move an object around in a gravitational field, it does not depend on the path that I take. As a little example, if I take this book, can't see it on the video right now, but if I take this book and lift it up here, I did a certain amount of work. The difference in work between, or the difference in energy between this spot and that spot does not depend on how I move it. If I take that and move it instead over like this, and then up like this, and then over like this, and move it to that position, the amount of work I did against gravity was the same. It's independent of that. Now, that is not true for friction law. If I move this book from Will over to here, that work done by friction, would you guys agree that work done by friction was negative? Would you agree that the amount of work done by friction is different if I move it through some convoluted path? Work done by friction does depend on the path taken. Now what's interesting about this is that I can get this work back. When I do work against gravity, I store that work as gravitational potential energy and I can get it back. Watch this. When I take this book over here and bring it over to this point, watch what happens. Are you ready? Why doesn't it go back? I did not store that work as a form of potential energy. So that work was lost. That work was done against friction, which doesn't store it as energy. When I do work against conservative forces, I can store it as potential energy. The elastic force is conservative. When you stretch or compress objects, the amount of work you do does not depend on the path that that elastic object takes. The electric force is really the same as the elastic force. So when you start talking about electric forces, second semester we'll start looking at how waves sort of act because of the electric forces between objects. Really the elastic force is electric. Other things, non-conservative forces, friction, air resistance, tension, cord, motor, a push or a pull, those are non-conservative. The work done depends on the path taken. Now, the reason we have that stuff there is because it leads into this concept of a conservation law. If there are only non-conservative forces, if there are no non-conservative forces acting, then the sum of the changes in kinetic energy and potential energy is 0. What that means is that KE and PE are going to change with equal but opposite signs. That allows us to define something called mechanical energy. And I'm going to write it down for you instead of going in that plane. Mechanical energy. This is not, by the way, the same as your ME score for your egg drop device. ME stood for material efficiency. This is mechanical energy. It is equal to the kinetic energy of an object plus the gravitational potential energy of that object plus the elastic potential energy of that object. It is the sum of those three forms of energy that we've modeled. How much energy of motion does it have? How much energy of position does it have due to a gravitational field or an elastic force that I'm doing work against? Now, the way that you might look at that up here is that energy is very general. There's mechanical forms, there's non-mechanical forms. Non-mechanical would be things like heat, things like chemical PE, things like nuclear PE, things like radiant energy, solar energy sometimes. Those are non-mechanical forms. The other forms are things that we've studied. Those three are what we call mechanical. Its conservation says that whatever I start with is what I have at the end. If I start with 28 units of energy, and there's only conservative forces acting, I end with 28 units of energy. They can be deposited into different forms, but the sum total should be the same. That allows us to do all sorts of very complicated kinds of things very simply. So I want to show you a few examples of that. These are where I start to do some of the classic demonstrations. Okay. So the big picture value is that if acceleration varies, if I have a non-constant force, could be due to gravity that's changing, or the slope of that roller coaster is constantly changing. If it's only gravity that's acting, I don't care which way that object moves. The gravitational force is the only conservative force doing work. That will allow us to be able to solve very complex problems. There could be lots of complex interactions occurring, but we're only interested in the final result. I just care about what goes on at the end. I don't care about all the details in between. I just want to know at the end. Now, I want to go through and do a couple of things here, which is showing you the map. Can you guys tell me what the mechanical energy is of this pendulum? What's the mechanical energy of this pendulum here? It's the sum of all forms of kinetic energy and potential energy. So I see that the total is 28. Anywhere I look through here, I should be able to tell you, you should be able to tell me what the other form of energy is, knowing what its energy is of the other forms. Let's just try it. Let's try it over here. And that position, it's swung through and it's all the way up to this particular spot. Its GPE at that point is 27 units. What should be its kinetic energy? It should be 1. And I know that because the total energy has to be the same. By the way, would you guys agree tension is acting on that pendulum? Tension is acting. Is it doing work? No, it's always perpendicular to the way the object is moving. So we only have a conservative force acting. How about this one? When its gravitational potential energy is 0, how much kinetic energy does it have? At this spot. 28, right? How about this one? When its kinetic energy is 32, it's below my reference position. How much gravitational potential energy does it have? It's really, I mean, guys, if I look at this from an energy standpoint, the sum total has to add to the same amount that I started with. This is why we use conservation laws. Okay, I want you to look at the roller coaster picture over on the right. Fill in every one of those blanks based on what you see. I want to know what the energy is in the various forms at the different locations. See if you can do it. I gave you the KE and GPE at that spot. You should be able to tell me everything else. Try it. once you have those numbers, will you share with that person that you're sitting next to, see if you are in agreement with them? So if you're having to watch this video from home, right now the students in my class are talking to each other about the numbers that go in here. If you're watching this, you should be trying this on your own and then see if you're correct. You guys agree this math is like, boy, give me more of this math, right? You want the heavy duty calculus kind of stuff, right? What are you struggling with here, Mike?
I just I know it's all supposed to add to 20 if that's a 10, but how do I know?
Such a key question here. Mike's asking a great question. Go.
How do I know how much of each equivalent?
So, gravitational potential energy, would you agree that depends on mass, depends on G, and depends on height?
Yeah.
At this position, you see its height is 0. That's my reference. So how much GPE does it have here?
Oh,
0. Therefore, how much kinetic energy must it have? It's got to be 20. And that's because all of the loss of GPE has been deposited into KE. If the only force doing work on this is a conservative force of gravity, by the way, there's a normal force acting. But that normal force is always perpendicular, correct? Which means it does no work on it. It doesn't change the energy of that object because it's not doing work. So the KE must be 20. How about here? It's halfway up from that position. Would you, maybe it's easier to do this one. Would you agree that it's at the same position as that one, so this must have the same energy configuration? It's got to be 10 units of kinetic and 10 units of gravitational. And that's because the energy is associated with where it is.
height-wise?
Yes, well, gravitational potential energy depends on its height, but the total has to be 20. How about this one here? It's halfway up. If this is a half the height, what must be the gravitational potential energy halfway up? Must be 5 units. So if that's the case, how much kinetic energy must I have there? The idea here, folks, is that the size of the energy pie has to stay constant. And as I change one, the other one offsets that. Now, I have a visual for you. And so the physics classroom, if you have not bookmarked this, sometimes people are like, I want a different way of seeing this. I want to show you some things about work and energy stuff. So here's energy transformation going downhill. Now I'm going to zoom in so you can see it a little bit better, I hope. Okay, so here we have a skier that's going from the top of the hill down that hill. You guys remember inclined planes and how difficult that was sometimes to deal with inclined planes? It had to do with force resolution, resolving the weight force into its components and Look again, the person at the very top starts with PE. As they slide down that hill, the PE loss is going into KE acquired. At the very bottom of the hill, you see how the W there is going to start showing in as a yellow? That's work done by friction, and work done by friction can remove mechanical energy. And so you notice that in this case, all we're doing is we're just sum totaling all those blocks. The energy that they start with gets converted into kinetic energy, and then once it gets to the bottom, all of its PE is now KE, and now I do some negative work on that from friction. And so what's the TME stand for, do you think? What's the TME stand for? Total mechanical energy. And in the beginning, the total mechanical energy stays constant because all I'm doing is gravity doing work on that changes energy from one form to the next. Let me show you another one. We've done some things with the spring-loaded dart guns. Let's show you the energy transformations for a dart gun. So here we have KE, that's the kinetic energy of the dart. We have PE, in this case is PEG, that would be gravitational potential energy. It started with elastic energy. Would you agree that it started with elastic energy? when I look at that, as it moves through the air, you can notice that the spring's elastic energy, which is yellow, the blue gravitational potential energy, and then the kinetic energy, they all add to the same amount. So if I just want to look at this from an energy standpoint, it becomes a lot cleaner to solve. TME, total mechanical energy, is a constant because the only thing doing work there is the conservative force of gravity or the spring. And so therefore mechanical energy just stays constant. Now, there's all sorts of other things that you could look at. I mean, there's, let's see, roller coaster, I guess so here's a visual for that. Again, you notice as this thing goes down and swings through those things, any loss of KE gets transformed into PE and so forth. Okay, so it's just a nice little principle to be able to show those things being conserved. Now, I'd like to at this point actually do some physical demonstrations. I'm going to stop the video. I'm going to stop the video recording after we answer this question. I'd like to get this one on recording. So will you take a moment and tell that person that you're sitting next to, after you've considered this, what the answer is to this question? 3 baseballs thrown from the top of the cliff along their paths, A, B, and C. If their initial speeds are the same, we're going to ignore air resistance. Thank you, non-conservative force of air resistance. We're going to ignore it. The ball that strikes the ground below with the greatest speed would follow which path? A, thrown up into the air. B, thrown horizontally. Or C, thrown downward, all at the same speed. Take a moment and tell that person that you're sitting next to which one will hit the ground with the greatest speed. Go. And if you are doing this from home, you should be trying to answer this question yourself. A is 1, B is 2, C is 3, D is 4, E is 5. I'm going to have you hold up a number of fingers that you think is the appropriate answer there. Not going to be on the recording. Now I want to see where you are with that. And once you have it, just show me here. Just show me like this. Show me where it is. No one else is looking. Not everyone's showing me that. All right. Some mixed answers. That's okay. This is new to us. But would you guys agree they all start with the same KE? All the same speeds. Do they all start with the same GPE? I mean, they're all starting right here. If I were to draw an energy pie up there, whatever speed I give it, whatever height I have it, it's got gravitational potential energy and it's got kinetic energy. And I don't care which way I throw it. By the way, energy is scalar. It has no direction associated with it. So I don't care if I throw its kinetic, don't throw it upward at an angle or the kinetic energy is the same regardless. Now, A deposits some of its kinetic energy into increased gravitational potential energy. So way up here, its kinetic energy is small and its GPE is much bigger. Whereas B, the size of that one is still the same size. Its kinetic energy is probably bigger than it was over here because it's speeding up a little bit. So let's do this. And C was thrown straight down almost. That size of the pie should be exactly the same as that, but its kinetic energy is even bigger because its height is so small. So its kinetic energy is really big. But when it all gets down here, what's the gravitational potential energy down at the bottom? It's all the same. It's all 0. So what that means is every one of these things has the exact same amount of kinetic energy, which is equal to the sum total of the energy that they had. The answer should be E. I don't care how that object moves from the hill down to the ground. The amount of energy stays conserved. Now, when you guys are solving projectile motion problems, wouldn't it be nice to just use energy stuff and having to go through instead of having to go through and do all sorts of like resolve the velocity into its components and things like that. This can be a very streamlined way of being able to analyze complex things simply. I'm going to stop the video there. Any questions for me before we go into the classic demonstrations? All right, I'm going to stop then. Hopefully, if you're having to watch this video, that made sense from home.